I finally got my first sponsor. Thanks Brilliant for sponsoring the video, and head over to brilliant.org/mathmaniac to get started for free with the interactive lessons. 1/0 is usually undefined, but why not define it? In some specific situations, it makes more sense to define this to be infinity than leaving it undefined. One of those situations is Möbius maps, which are functions of the form az plus b over cz plus d, where a, b, c, d are some complex constants, and we are going to impose that ad minus bc is not 0. This restriction ensures that if c is 0, d cannot possibly be 0, otherwise ad minus bc would be 0. As a result, in this case, the denominator would never be 0, and we have a nice linear function. However, if c is not 0, then we have a problem, because the denominator could be 0. This happens precisely when z equals negative d over c, and in that case, we define f of negative d over c to be infinity. However, we would also define f of infinity to be a over c, essentially the limit of the function when z tends to infinity. Back to the c equals 0 case, we also define f of infinity, this time the value being infinity. These different cases can essentially be summarized as f of infinity is a over c, and anything non-zero divided by 0 is infinity. The reason why this condition is required would be shown later. Now you might be asking a question, why do we need to torture ourselves by letting infinity into the picture? Well, I don't know, mathematicians sometimes want to torture themselves. Just kidding. Or am I? By the end of this video, hopefully you can see the reason why sometimes treating infinity as a number isn't so bad. During the course of the video, we will first have a good intuition of Möbius maps in 2D, then to 3D, where Möbius maps can be more naturally explained. Let's first focus on a special case, 1 over z, or if you prefer, a, b, c, d are 0, 1, 1, 0 respectively. If we write z in its polar form, then its inverse can be written down pretty easily. Now let's see what this really means. Negating the argument means reflecting across the real axis. But what about inverting the radius? This is a classic transformation in Euclidean geometry, inversion with respect to the unit circle. If you watched this previous video on problem of Apollonius, you know some properties of inversion, but here is a quick recap. The official definition of inversion is that given a point and a circle, we construct a ray from the center to that point. Somewhere along this line, there is a point where the product of the distances from the center is the square of the radius of the circle. In our case, we are dealing with a unit circle, so the radius squared is 1, and so the moduli really are inverses. But this is the more general case. We can also invert any other object like a circle. That means for any point on the circle, we can invert that point, and do the same for all the other points. The result is still a circle. In fact, in general, circles always map to circles if we think of straight lines as a special kind of circle with infinite radius. A brief explanation of this fact was given in this video. But rather than treating straight lines as circles with infinite radius, think of it this way. This green line is the image of the blue circle under inversion. The reason why the image is not a traditional circle is that the blue circle passes through this red dot, the center of this yellow circle we are inverting with respect to. Now what does this point invert to? By definition, the image distance b is radius squared over a. At the center, the original distance a is 0, so b would be something over 0, which is infinity, so the image is infinitely far away. By abuse of notation, we call that image point infinity as well. So a circle passing through this red center maps to another circle passing through the image of the red center, which is infinity. I know that this all sounds ridiculous, but I promise that when we get to 3D, everything will make a lot more sense. Anyway, the main takeaway is that under inversion, circles are mapped to circles if we accept that straight lines are just circles passing through infinity. However, there are way simpler transformations that have the same property. For instance, translation obviously maps circles to circles. Rotation also works. And reflection. And enlargement and shrinking. So all these transformations preserve circles, and of course, any combination of these would as well. The combinations of all these are precisely the Möbius maps and their conjugate. But let's focus on Möbius maps, i.e., why are Möbius maps just some combinations of these? First, we said before that the complex Z-inverse is just a combination of reflection and geometric inversion, so this operation does map any circle to some other circles. Then all we need are some algebraic manipulations. The reason we do this is to see that Möbius maps are just, first, translation by the complex number d over c, then by putting it in the denominator, it is the complex inversion. Then we multiply by some complex number, which is some stretching or squishing and rotation. Finally, we do another translation. All these operations preserve circles, so Möbius maps have to preserve circles as well. Now, since some of you want me to put in some exercises in videos, here are something to ponder. This decomposition only makes sense if c is not 0, so what happens if c is 0? In the beginning of the video, I said we need AD minus BC not equal to 0. Can you see why now? There is a final question, which is more difficult. This shows that any Möbius map is a combination of these 5 transformations, but do we need all 5? Is it possible that rotation might just be some weird combination of translation and inversion or something like that? Leave your answers in the comments below. Anyway, when you see these transformations, you should expect the end result to be all circles. Otherwise, there must be something wrong. However, the transformation looks a bit too complicated to understand. Is there an easier way? Yes, but before we get into that, we have to learn geometric inversion a lot better. This chapter will establish several properties of inversion, but I'm only going through the sketch of the proofs because ultimately the last property is the only one that we will need. To be honest, in general, proving a big theorem is like going through an unfamiliar route towards a destination. A lot of times, proofs are either like really small step-by-step instructions, which in some cases are really needed, but it quickly drains your motivation. Or the proofs are way too big of a leap, like in the memes where proofs of big theorems are left as an exercise. The better way, I think, is to place some reachable checkpoints along the way, not too far or close from each other, and more importantly, telling you ahead of time the checkpoints you are going to get to, and then if needed, provide the step-by-step instruction. This will keep you motivated because you know what to look forward to. Anyway, enough with the rant. This would be the really big picture, and we will have smaller checkpoints along the way. Don't worry about the fine details in the first go and feel free to pause at any point. First up, we have a big word here, anticonformal, which means that given any two intersecting curves, when you do the geometric inversion, we have another pair of intersecting curves, and importantly, the angles remain unchanged after inversion. However, if we distinguish the curves, like here, when same colored curves are images under inversion, and we assign orientation of angles, like here, measuring from green to blue clockwise, then after inversion, it goes from green to blue anti-clockwise, and so inversion reverses orientation of the angles. Being anti-conformal is just a succinct way of saying both angle preserving and orientation reversing. But why is inversion anti-conformal? Ultimately, the intersecting curves are characterized by their tangents at intersection, so we can just focus on this case. The good thing is that we know what lines get mapped to, namely circles passing through the center. To check that this angle is the same as the original one, we can check that the one at the center is the same as the original one, but I will leave that up to you. Next up, we have orthogonal circles fixed. This essentially means that if the blue circle intersects the yellow one orthogonally, then inversion in the yellow circle leaves the blue circle unchanged. The points can map to some other points, but it still ends up on the original circle, so the overall figure hasn't changed. The idea to prove this is that the tangents to the blue circle passes through the red center, and also power of a point theorem, which is, well, a powerful theorem, but not too difficult to prove either. Now, is the converse true as well, i.e., are circles that are fixed orthogonal? Well, apart from the yellow circle itself, the answer is yes. The idea is to zoom into the intersection and note that the outward ray from center would be perpendicular here. So if the intersecting angle is not a right angle, then points on the left would be inverted to some point on the left, and so the circle would not be fixed after inversion. With all these, you can derive that any circle passing through inverse points has to be orthogonal to the original yellow circle, and that intersections of any pair of orthogonal circles have to be inverse points. Using this, we can even define inversion across a line. Given a point, we can construct orthogonal circles passing through that point, and the other intersection would be the inverse point. But this point is precisely the point after reflection across the line. For the curious among you, here is another thing to ponder. Reflection can also be seen as the limit of inversion when the radius tends to infinity. Can you prove this? Anyway, that leads us to the third and final property. As before, the yellow circle is what we are inverting with respect to, and the blue circle and two green points are going to be inverted. These green points are inverse or symmetric points with respect to the blue circle. It turns out that after inversion, the 2 points are still inverse or symmetric to each other. This is relatively easy once we have the previous properties. First off, we construct circles passing through those 2 points. By our previous properties, these circles have to all be orthogonal to the blue circle. Now invert everything with respect to the yellow circle. Because inversion preserves angles, these have to be right angles, and so the intersections of these orthogonal circles have to be inverses to each other. With this done, we go on to 3D. We have defined geometric inversion in 2D, but there is nothing in 3D that stops us from doing this. Given a sphere, points that are inverse to each other have to lie on the same line, and the distances also multiplied to the radius squared. Given how similar these situations are, lots of properties that we have seen before would generalize. In 2D, inversion sends circles to circles, and the 3D analog would be sending spheres to spheres. And straight lines will be generalized to planes, i.e., planes are just spheres passing through infinity. With this in mind, let's consider this case. This yellow sphere, as always, would be the reference, and we want to invert this blue sphere. Since the blue sphere passes through the red center, we know that it would be a plane after inversion. But which plane? All the points at this intersection have to be fixed, so the plane has to pass through the intersection. So this purple plane is the image after inversion. But what does this really mean? If you have a point on the sphere, we know that the inverse has to lie on this ray. But because we know that the image is the plane, the intersection would be the image. If the point is below the plane, then we again consider the intersection of this ray and the plane. And even though it is phrased as spherical inversion, this process is much more commonly known as stereographic projection. Now, if you haven't watched the previous videos, here is the concept of the Riemann sphere. Essentially, think of the complex plane in 3D as well as the unit sphere centered at the origin. Then for any complex number on the plane, we do the inverse stereographic projection onto the sphere. So if this point represents 1.2 plus 1.3i, then the green point on the sphere would correspond to the same complex number. Under this correspondence, the sphere would be called the Riemann sphere. What we have said is simply that this can be thought of as spherical inversion with respect to the orange sphere, and so this point should correspond to infinity. And here comes the fun part. In the previous chapter, we established that inversion preserves symmetric points, so if we have two symmetric points with respect to the yellow unit sphere, then after inversion, these 2 points are still symmetric, but across the plane, because the plane is the image of the yellow sphere under inversion. Let's unpack what this means. Being inverse points across the unit sphere is the same as inverse points across the unit circle on the complex plane, and doing the inversion is the same as projecting back onto the Riemann sphere. So on the complex plane, inversion across the unit circle corresponds to reflection across the equatorial plane for the Riemann sphere. Isn't that amazing? Let's put this aside for a moment. Consider instead two symmetric points across a line. After projecting back onto the sphere, these two green points are symmetric to each other, but across this vertical plane instead. So on the complex plane, reflection across the line corresponds to reflection across a vertical plane for the Riemann sphere. You might have guessed what's coming. Remember that 1 over z is composed of reflection across the real axis and inversion across the unit circle. And so on the Riemann sphere, it is a combination of reflection across the equatorial plane and reflection across the vertical plane. The combined effect of these two reflections would be rotation along the real axis by an angle of pi. This might not be obvious, but you would only need a bit of thought on another vertical plane. But the fact that 1 over z corresponds to simply rotation of the Riemann sphere should be somewhat mind-blowing. This also means that the south pole, which corresponds to the complex number 0, should be rotated to the north pole, which corresponds to infinity. So in this context, it is very natural to define 1 over 0 to be infinity. So far, we have established that 1 over z is a rotation of the Riemann sphere. but in general, Möbius maps also include adding and multiplying by some constant complex numbers. Let's focus on translation first. This is how it looks on the Riemann sphere, but it looks a bit too complicated. To make it simpler, we cheat a little bit. Instead of having a stationary Riemann sphere, we can simply translate the Riemann sphere itself and stereographically project from the North Pole to get the corresponding complex number. So that's adding sorted. Just like in 2D, we can translate the Riemann sphere. What about multiplying a complex number? For now, focus on stretching and squishing. It turns out that there is a simple cheat to represent this, simply moving the Riemann sphere up and down. The sphere can go up indefinitely, but the North Pole has to be higher than the plane to do the stereographic projection. The height of the North Pole dictates the scaling factor, the stretching or squishing. So that's how you can deal with multiplying the modulus of a complex number. But what about rotation? Turns out this is quite simple. A rotation about the origin on the complex plane corresponds to a rotation about the vertical axis on the Riemann sphere. So every simple transformation here is sorted. Translations on the complex plane are horizontal translations of the Riemann sphere, and enlargement and shrinking are vertical translations of the sphere. Rotation is, well, rotation on the sphere, but about the vertical axis. And the complex inversion is rotation about the real axis. Unfortunately, when you compose two functions, the resulting transformation on the Riemann sphere is not that straightforward. For instance, this should be a combination of translation and rotation about the real axis, but it just isn't true. Still, it isn't actually awful, and in fact, in general, any Möbius map corresponds to some rigid motion of the Riemann sphere. So the translations and the rotations we have identified are just simple examples of rigid motion. And this correspondence is 1-to-1, so any Möbius map can be uniquely represented by a rigid motion. This amazing result is established in this paper published in 2012. I'm just really surprised that this isn't discovered earlier, so if you can find a paper that explicitly demonstrates this unique correspondence earlier than 2012, please let me know. While Möbius maps are interesting in its own right, they have a few important applications or connections worth a brief mention. For the slightly more theoretical side, the most direct use would be in hyperbolic geometry. Just like in Euclidean geometry, where translation, rotation, and reflection and the combinations of those are the distance-preserving transformations, in hyperbolic geometry, the Möbius maps and their conjugates are the distance-preserving transformations. Möbius maps are also the simplest examples of conformal mapping, which are hugely important in physics, especially fluid mechanics. But the most surprising of all, Möbius maps are related to special relativity. The show-off explanation is that these two groups are isomorphic, but to understand it more deeply, check out this book and also this YouTube video where the author Sir Roger Penrose himself talked about the book. Now you might notice that I gave a lot more exercises in this video because practicing is the only real way to get good with maths, which is exactly what Brilliant is trying to do as well. They have interactive lessons in all the STEM subjects with more than 60 courses to choose from. For example, if you want to learn more about the power of a point theorem I mentioned before, you can do so in the Geometry 2 course. Or if you want to understand the relationship between special relativity and Möbius maps, you can learn more about special relativity in Brilliant. This is the bit about causality, but the course can get quite deep, all the way to 4 vectors and 4 momentum conservation. To sign up for Brilliant, head over to brilliant.org/mathmaniac to get started for free, and the first 200 viewers will get 20% off their annual membership. Thanks Brilliant for sponsoring this video, and the patrons for supporting the channel. If you enjoyed this video, don't forget to subscribe with notifications on, and like, comment, and share the video as well. See you next time.